The substance you drink every day, bathe in, watch fall as rain, water, doesn't behave the way physics expects it to. If you looked at its chemical structure and tried to predict what it would do, almost every prediction would be wrong. The boiling point is wrong. The density is wrong. The surface tension is wrong. The heat capacity is wrong. Water plays by different rules than the rest of the universe. And every single one of those anomalies is something that had to be exactly right for life to exist. Let's start with what water is supposed to be. Chemically, it is a small, simple molecule. Two hydrogen atoms bonded to one oxygen atom, H2O. In chemistry, you can predict how a molecule will behave by looking at its neighbors in the periodic table. Water belongs to a group called the chalcogenides: oxygen, sulfur, selenium, tellurium, all forming similar molecules with hydrogen. Hydrogen sulfide, hydrogen selenide, hydrogen telluride. If you plot the boiling points of these compounds against their molecular weight, they line up perfectly on a smooth curve. Each heavier molecule boils at a higher temperature, just as chemistry predicts. And if you extend that curve down to where water should sit, based on its molecular weight, water should boil at around -80 degrees Celsius. It should be a gas at room temperature. It should never form oceans, rivers, or rain. The fact that water is a liquid at the temperatures where life operates is, chemically speaking, already a violation of everything its molecular weight predicts. Water boils at 100 degrees Celsius. That is 180 degrees higher than it should. Not slightly off. Not a small correction. 180 degrees of pure anomaly. The largest deviation from predicted behavior of any common substance in chemistry. The reason for this deviation is something called hydrogen bonding, and it is one of the most consequential features of the universe. Oxygen is strongly electronegative. It pulls electrons toward itself with unusual force. In a water molecule, this creates an uneven distribution of charge. The oxygen end of the molecule is slightly negative, and the hydrogen ends are slightly positive. This means water molecules are polar. They have an electrical imbalance. And because they are polar, they are attracted to each other. The slightly positive hydrogen of one water molecule is drawn toward the slightly negative oxygen of another. This attraction is a hydrogen bond, and it is much stronger than the weak attractive forces between most small molecules. Hydrogen bonds are why water molecules cling to each other with unusual stubbornness. They are why water takes so much more energy to boil than its molecular size would suggest. They are the reason liquid water exists at all at the temperatures where biology operates. But hydrogen bonding is just the beginning. The anomalies go much deeper, and several of them are strange enough to qualify as outright violations of what chemistry and physics would predict. Take density. For almost every substance in the universe, the solid form is denser than the liquid form. This seems obvious. Freezing should pack molecules more tightly together, increasing density. And it works exactly this way for iron, copper, glass, alcohol, and essentially everything else. When these substances freeze, they sink in their own liquid. But ice floats on water. You already knew this, but you may never have stopped to find it strange. Ice is less dense than liquid water. When water freezes, it actually expands, becoming about 9% less dense than the liquid. This is because when water molecules form the crystalline lattice of ice, the hydrogen bonds force them into a hexagonal arrangement that is more open, more spread out, than the relatively disordered arrangement of liquid water. The solid takes up more space than the liquid. The ice floats. This seems like a curiosity until you think about what it means for a lake in winter. If ice were denser than water, as it should be according to the normal rules, ice forming at the surface would sink. New water exposed at the surface would then freeze, sink, and the process would continue until the entire lake froze solid from the bottom up. Aquatic life would be extinguished. But because ice is less dense than water, it floats and forms an insulating layer at the surface. The liquid water beneath is protected. Life continues. Lakes, rivers, and polar oceans do not freeze solid in winter. Not because of luck, but because of this single anomaly in water's density. Every fish that has ever lived in a frozen-over lake owes its existence to the fact that ice floats. And ice floats because hydrogen bonds force water molecules into an open hexagonal lattice when they freeze. The anomaly is not accidental. It is structural. Now consider heat capacity, the amount of energy required to raise a substance's temperature. Water has an extraordinarily high heat capacity. It takes more energy to heat water by 1 degree than to heat almost any other common substance by 1 degree. This also shouldn't be the case for such a small molecule. Normally, small light molecules heat up quickly. Water is slow to heat and slow to cool. It resists temperature change more stubbornly than almost anything else. Because of this, the oceans act as an enormous thermal buffer for the planet. They absorb heat slowly and release it slowly. Coastal climates are moderate because the ocean nearby is reluctant to change temperature. The entire global climate system depends on water's anomalous heat capacity to avoid wild temperature swings that would make the surface uninhabitable. A planet covered in a liquid that heated and cooled as quickly as its molecular size suggested would experience temperature extremes that would sterilize it. Water's anomalous heat capacity is not separate from the conditions for life. It is one of the conditions for life. Then there is surface tension. Water has the highest surface tension of any common liquid. This is again a consequence of hydrogen bonding. Water molecules at the surface are pulled inward by their hydrogen bond network with the molecules below them, creating a film at the surface that resists penetration. This is why water forms droplets rather than spreading in a thin film. It is why a needle can float on water if placed carefully. It is why the meniscus curves upward in a glass tube, a phenomenon called capillary action. And capillary action is not a laboratory curiosity. It is how water moves against gravity inside trees. The sap in a redwood 300 feet tall doesn't have a pump. Water climbs to the top of that tree through capillary action, the surface tension of water pulling it upward through narrow conduits in the wood against the force of gravity. Every tall plant on Earth depends on water's anomalous surface tension to move water to its highest leaves. Remove that anomaly, and all vascular plants collapse. Wait, because the density anomaly goes even stranger than just ice floating. Water has a maximum density not at its freezing point, but at 4 degrees Celsius. As water cools from room temperature down to 4 degrees, it becomes progressively denser, as expected. But then, from 4 degrees down to 0, as it continues to cool before freezing, it begins to expand again and become less dense. This means that in a cooling lake, water at 4 degrees sinks to the bottom, while colder water stays near the surface. The deepest water in a lake in winter is 4 degrees. Not 0, not frozen, 4 degrees. This is the temperature at which certain organisms, particularly some species of fish and bacteria, have evolved to survive. The bottom of the lake is a refuge not in spite of the physics of water, but precisely because of it. Water does not simply freeze from the top. The unusual density curve means that even beneath an ice cap, there is liquid water at 4 degrees, waiting at the bottom. The anomaly is layered. Ice floats, but also liquid water parks itself at 4 degrees at the greatest depth. Life finds a way because water behaves unusually at every relevant threshold. Now consider what happens when water evaporates. Water has an extremely high latent heat of vaporization, the energy required to convert liquid water to vapor. It takes an enormous amount of energy to evaporate water compared to other liquids of similar molecular size. This is why sweating works. When water evaporates from your skin, it carries an outsized amount of heat with it, far more heat per gram than a simpler liquid would. This makes sweating one of the most effective cooling mechanisms in biology, and it works specifically because of water's anomalous heat of vaporization. This same property is why large bodies of water don't simply evaporate rapidly in sunlight. The energy required to evaporate them is enormous, stabilizing the water cycle that moves fresh water around the planet. A liquid that evaporated easily at biological temperatures would not form the kind of stable hydrological cycle that life on a planetary surface requires. Water's stubbornness about evaporating is a feature, not an inconvenience. Here is the point at which this stops being chemistry and becomes something deeper. Consider what it means for water to be the universal solvent. DNA carries genetic information as a sequence of base pairs. But DNA only works inside a water environment. The double helix is held in its shape partly by hydrogen bonds between base pairs, but also by the interaction of the molecule with surrounding water. Remove the water, and the helix collapses or denatures. The proteins that catalyze every chemical reaction in your body, enzymes, are folded into precise three-dimensional shapes. That folding is determined largely by which parts of the protein are hydrophilic, water-attracting, and which are hydrophobic, water-repelling. The protein folds to hide its hydrophobic regions from water and expose its hydrophilic regions. Without water, there is no driving force for protein folding. Without folded proteins, there are no enzymes. Without enzymes, there is no metabolism. Without metabolism, there is no life. Water is not just the medium in which biology happens. It is the structural framework that makes biological molecules work. Take it away, and the molecules themselves stop functioning. Not because they are damaged, but because the interactions that give them their shapes and functions depend on water being there. Scientists have cataloged more than 70 distinct anomalies in water's behavior, physical and chemical properties that deviate from what its molecular structure predicts. Many of these anomalies are related to hydrogen bonding, but not all of them are fully explained, even now. Water's behavior under extreme pressure is still not completely understood. The precise structure of liquid water at the molecular level, how hydrogen bond networks form, break, and reform over picosecond timescales, is still an active area of research. Water is the most studied molecule in the history of chemistry. It is also still, in certain respects, not fully understood. The simplest molecule in biochemistry is also one of the most physically peculiar substances in the universe. There is another layer here that tends to be overlooked. Water is not merely an anomalous liquid. It is anomalous in a way that is almost perfectly tuned for chemistry. Its polarity makes it an excellent solvent for ionic compounds. Salts dissolve in water, releasing ions that can participate in electrochemical reactions. Its hydrogen bond network makes it an excellent medium for proton transfer, the movement of H-base ions from one molecule to another, which is the basis of acid-base chemistry and a central mechanism in cellular energy metabolism. The fact that water itself ionizes slightly, splitting into H- and OH-, gives it the capacity to act as both a weak acid and a weak base, buffering biochemical reactions against extreme pH changes. All of these properties are directly related to hydrogen bonding, and all of them are necessary for biochemistry as we know it. A solvent that had some of these properties, but not others, would not support the full complexity of cellular chemistry. Water has all of them, simultaneously, in a molecule of 2 atoms of hydrogen and 1 of oxygen. This creates an uncomfortable question. Is it a coincidence that water, the specific molecule that forms the solvent for all known life, happens to have exactly the right anomalies for life to be possible? The density anomaly makes lakes habitable in winter. The heat capacity anomaly stabilizes planetary climate. The surface tension anomaly moves water against gravity inside plants. The evaporation anomaly makes sweating work as a cooling mechanism. The hydrogen bonding that causes all of these anomalies also makes water an extraordinarily effective solvent, the best solvent known for ionic compounds, which is why all biochemistry happens in water. Every anomaly points in the same direction, toward habitability. It is as if water was designed to be the molecule of life. But of course, it wasn't designed. So what is the explanation? There are 2 ways to approach this. One is the anthropic argument. We observe water to be life-compatible because we are here to observe it. If water had different properties, we wouldn't exist to notice. There might be universes where water behaves differently, and no one asks the question. This argument is logically valid, but philosophically unsatisfying. It explains why we observe what we observe, but it doesn't explain why the universe happens to contain a molecule with this specific combination of anomalies. The other approach is to recognize that the anomalies are not independent. They all flow from a single source, the hydrogen bond. The polarity of the oxygen-hydrogen bond, the electronegativity of oxygen, the specific geometry of the water molecule. These are the underlying physical facts, And the 70-plus anomalies are consequences. You don't need to invoke design to explain water. You need to understand hydrogen bonding deeply enough to derive the consequences. And when you do, you find that a molecule with the geometry and electronegativity of water could not have been otherwise. The anomalies are not lucky accidents. They are mathematical consequences of the specific atomic physics of oxygen and hydrogen. But that only pushes the question back one level. Why does hydrogen bonding work the way it does? Why does oxygen have the electronegativity it has? Why is the geometry of the water molecule the angle it is? 104.5 degrees between the two hydrogen atoms, not 90 degrees, not 120 degrees, but precisely this angle, which is what produces the optimal geometry for hydrogen bond network formation. The answer to that question lies in quantum mechanics, in the wave functions of electrons, in the hybridization of oxygen's atomic orbitals, in the Pauli exclusion principle operating at the scale of individual electrons. The molecule is what it is because the atoms are what they are. The atoms are what they are because the laws of quantum mechanics are what they are. You can trace the life compatibility of water all the way down to the values of fundamental physical constants. And at that level, the question of why those constants have the values they do is still open. This is the kind of question that physics keeps encountering when it goes deep enough. The specific properties of water are not accidental in the sense of being random. They follow with mathematical necessity from the underlying physics. But the underlying physics could, in principle, have been different. A universe with a slightly different fine structure constant would have different chemistry. Different chemistry might produce no molecule with water's combination of properties. And without something playing water's role, the conditions for the kind of complexity that produces biology, self-replicating molecules, information storage, thermodynamic gradients, solvent chemistry, might not be achievable. Whether this means anything profound about the universe is a question physics cannot currently answer. Some physicists are comfortable treating it as a brute fact. The constants are what they are, and we find ourselves in a universe where they support chemistry complex enough for life. Others find this unsatisfying. Physicist Lawrence Henderson, writing in 1913 in a book called The Fitness of the Environment, argued that water and carbon dioxide are so remarkably well suited to supporting life that the fitness of the environment for life is as real and as significant as the fitness of organisms for their environments. Darwinian evolution explains how life adapts to its environment. But what explains why the environment, at the chemical and physical level, is so extraordinarily suited to life? Henderson had no answer. A century later, neither do we, fully. But the question has sharpened considerably. We now know exactly which properties of water deviate from predictions, and by how much. We know which of those deviations are necessary for which biological functions. We can trace the deviations to hydrogen bonding, and the deviations in hydrogen bonding to quantum mechanics. The chain is now almost fully mapped. Only the final link, why the laws of quantum mechanics have the specific values they do, remains open. It can trace the chain from the fine structure constant to electron orbitals, to molecular geometry, to hydrogen bonding, to surface tension, to capillary action, to the height of a redwood. The chain is unbroken. But at the end of that chain is a fact about fundamental constants that remains unexplained. Here is what tends to land when you really follow this chain all the way. You pour a glass of water. The water in the glass is room temperature, liquid, unimpressive. But look at what is happening inside that glass at the molecular level. Billions of water molecules are moving, colliding, forming hydrogen bonds with their neighbors and breaking them on timescales of picoseconds, trillionths of a second. The hydrogen bond network of liquid water is not static. It flickers continuously, molecules constantly reorganizing into new configurations. This flickering network is why water is such a good solvent. Ions and polar molecules can be surrounded, stabilized, and carried by the dynamic network. It is also why water's structure is so difficult to study. By the time an experiment resolves one configuration, the molecules have already moved on to another. The glass of water is not a passive object. It is an enormously complex, constantly reorganizing molecular system. and its behavior at every scale, from the picosecond flickering of hydrogen bonds to the millimeter scale of the surface meniscus to the kilometer scale of ocean heat capacity, is governed by a set of anomalies that together define the conditions for life. Water does not violate physics. It obeys physics more precisely and completely than any other common molecule we know. But it obeys a very specific, very unusual combination of physical rules. And the consequences of those rules are what the rest of nature and life is built on. When you understand why ice floats, you understand why there are fish in Arctic lakes. When you understand surface tension, you understand how trees grow tall. When you understand heat capacity, you understand why you can live near an ocean. And when you understand hydrogen bonding, the root cause of all of it, you understand that the most ordinary molecule on Earth is also one of the most precisely constructed things in the known universe. If there is something about water that you will never quite see the same way after this, the way a glass of it feels, the way rain looks, the moment you notice ice floating in a drink, leave a comment. What landed hardest? The density anomaly? The fact that life depends on ice floating? The idea that 70 anomalies all trace back to one molecular property? Or just the scale of it? The chain from electron orbitals to Arctic lakes to the existence of every fish, plant, and person that has ever lived. And if you want to keep following chains like this, from ordinary things to the physics underneath, subscribe, because that is exactly what this channel is here for.